Welcome everyone to the AI Research Bites. This series of short and informative talks showcase cutting-edge research work from ServiceNow AI Research team. The AI Research Bites are open to all, especially those interested in keeping up with the fast-paced AI research community. Today's session features a 15-minute talk from DJ Dvijotom and will be followed by a 10-minute Q&A. DJ leads the AI Trust and Security Research team at ServiceNow AI Research. He previously worked in the area at DeepMind and Pacific Northwest National Laboratory. His research has won several Best Paper Awards, including most recently at ICML and CVPR 2024, and it was also awarded a bug bounty by OpenAI's security team. So we are very excited to welcome you, DJ, to present your work today.
Thanks a lot, Fanny, and thanks everyone for joining. It's a pleasure to share our work. I should start by acknowledging my wonderful collaborators. This work was led by student Abhinandan Bose at the University of Washington, his advisor, Mariam Fazal, and Laurent Assad, who's faculty at Northeastern. So we should start by saying that this is research work and it represents forward-looking statements as far as ServiceNow is concerned. So let's start by thinking a little bit about how we train AI systems today. There's typically two phases of training. There's a pre-training phase where you try to get your hands on all kinds of data, scrape the web perhaps, and then train like a really powerful foundational model on all of this data. And then you have a model which is very good at a general understanding of the world, but to make it useful towards specific tasks, you need a post-training phase where you could have you in sub-phases where you first collect a bunch of instruction tuning data that teaches the model how to behave, say, specifically as a chatbot or as an agent. And then you also might have an reinforcement learning from human feedback loop, where you make the model interact with real users and collect feedback from them on how the model is doing. From a security perspective, this represents a bunch of potential risks. The one that's been studied most of the time in the security literature so far is what we would call static poisoning attacks. This is a situation where you're scraping the web potentially for data, and some of this data could come from untrusted sources. There might be malicious entities that are trying to put data on the web so that when a model is trained on that data, it has a specific behavior, maybe specific kinds of political bias or specific kinds of favoritism towards certain races or genders or those kinds of things. The situation here is that the adversary gets to influence this whole system once, where at the beginning of the training, where data is being collected, some of the data is influenced by the adversary, right? And this kind of attack was pioneered in this paper that actually won a Test of Time award at ICML a few years ago, where they showed that very simple forms of AI by today's standards support vector machines. The single layer neural network are actually sensitive to this kind of risk potentially. More recently, there's been work that shows that modern AI systems like CLIP and other similar image embedding systems are also vulnerable to this kind of attack. This is potentially a risk even for AI systems of today. So this kind of poisoning could have various targets. The one that was considered, say, in the Biggio paper is to decrease the prediction accuracy or increase the error rate of the AI. But more worryingly, you could have AIs to take specific political biases, or even more worryingly for an enterprise like ServiceNow, you could embed backdoors into the AI that behave such that the AI does the right thing most of the time. But then in very specific situations, it triggers some very malicious behavior, like leaking all the data that it's collecting from a user. As opposed to the static attacks, we are interested here in dynamic attacks, where the poisoning happens actually in the post-training phase, where you're collecting human feedback from users that are using the model, because the users maybe not always people that you trust, there may be certain users who are trying to deliberately provide harmful feedback to the model, again, to steer it in the same ways that the static poisoning attacks do. So the key finding from some prior work is that actually dynamic poisoning attacks are more powerful from an attacker's perspective. So there was this work from 2018 that showed that if you compare the red curve and the blue curve, on the y-axis is how accurate the model that you train is, and on the x-axis is the fraction of data that is poisoned. You can see that the blue curve, which represents a dynamic poisoning attack, has a lower accuracy, especially once the fraction of poisoned data points crosses 20%. And the red curve degrades more gradually, showing that essentially dynamic poisoning attacks are strictly more powerful than static attacks. So the question is, how does this impact today's AI systems, and how do we defend against these kinds of attacks? So a key concept in AI security is this notion of certificates, which underlies the idea that we may not know exactly what the attacker does. We don't know exactly what kind of data they're going to be using to poison the model. So we may not be able to make very good assumptions on that. But certificates try to achieve an objective which says that no matter what the attacker does, the impact on the AI should be limited. And their mathematically rigorous limit on the worst case impact of the attacker, right? So we're saying that we don't know exactly what the attacker is going to do, but no matter what they do, this is the worst case influence they can have on the AI. And there's been a lot of work in the static poisoning space. In particular, there's this paper that came out at NeurIPS a few years ago, and then lots of follow-up works. But all of this work only applies to static attacks and does not address this more dynamic scenario that we're interested in. So we propose certificates of robustness for dynamic poisoning attacks. That's the key contribution of our work. And in order to explain what this certificate looks like, I'm going to introduce a few concepts. So we are interested in the behavior of a learning algorithm, which could be some form of stochastic gradient descent. It could be some form of reinforcement learning. And typically, we look at the algorithm as receiving a data point zt at time t. And maybe this could even be a batch of data points. We don't make any such specific assumptions. And then the model parameters are updated from theta t to theta t plus 1 by applying the learning algorithm. And learning proceeds iteratively in several rounds of learning. Right? And what we do is we consider what's called a Huber poisoning model. Sorry, there's a typo here. It should be Huber, no T. The data that you receive is good data with probability 1 minus epsilon and bad data with probability epsilon. And the adversary that's generating this bad data essentially is interested in some kind of adversarial objective that controls the long-term impact that the adversary has on the learning algorithm. In order to decrease the accuracy of the model, for example, the adversarial loss would be the prediction error. In order to embed a backdoor, it would be basically what's the probability that the model decides to leak some confidential data when it knows that the user of the model is, say, a CEO of a company. And maybe you want to embed some political bias, in which case the adversarial target would be the probability of bias towards some target party, right? And so there's all of these components that set up the problem where we apply an iterative learning algorithm. In each step, we get some data, which is poisoned with some probability epsilon. And then the attacker that's trying to design that poison data has a long-term objective that's trying to achieve some target, embed a backdoor, or decrease accuracy. And so in light of this formulation of the problem, the main result that we have, which is the technical contribution of this work, is that for any function lambda, we are able to show that the worst case impact of the adversary, which is basically an upper limit on the adversarial objective, is this quantity, which is the expected change in this lambda function at step t. Plus the immediate adversarial impact. So essentially, what was the impact of the adversary at time t, right? And so you can see that we went from like considering a very long-term objective, which requires you to like simulate the behavior of the learning algorithm over many, many steps, into kind of a single shot objective where we say that we consider a single step of the learning algorithm, and then we just need to look at the change in this function lambda and add this impact of the adversary. And the worst case value of this over all choices of the bad data gives the certificate. So what we know is that no matter what strategy the attacker chooses to decide what the ZT should look like, this quantity that the attacker is trying to optimize is going to be upper bounded by this value. And we can discuss more later potentially on how this lambda function can be designed, but the choice is kind of critical. So once we have this robustness certificate, then the natural question is, okay, how do we use it to design a more secure learning algorithm? The idea is to think about some kind of meta-learning setup where you have a learning algorithm that's trained using a combination of poison and benign data. Based on the fraction of poison data, you can come up with this robustness certificate, and you can basically ask for an upper bound on this worst case adversarial objective, which is essentially what the certificate is. And then you can use meta learning to tweak the learning algorithm so that this worst case certificate gets better, right? And you can balance the overall behavior of the learning algorithm in the absence of poisoning, which is maybe like a benign setting, with the worst case impact of the poisoning. And then that allows you to design a learning algorithm that's more secure. So how well does this work? We are able to show that this is actually able to create more accurate and secure learning algorithms. For this data called help steer, which is a common data that's used to train reward models that go into RLHF, we consider the scenario where an adversary can poison some fraction of this data set. We consider up to 5% of poisoning. And we show that essentially, if you use our best certificate and design the learning algorithm, then the prediction error in the reward function that you learn is essentially how accurate the reward function is, seems to grow in a more mild fashion. And in fact, like the certificate is a theoretical upper bound, but we show that there is actually an attack that achieves something that's pretty close to the upper bound. So the theoretical upper bound is actually not that far off from what a real attacker is able to do. If you contrast that with the red curves, those are essentially what you would do if you did not use this meta-learning paradigm to design a secure learning algorithm. So you would have a much higher error rate because of the impact of the attacker. And indeed, there is a real attack shown in the dashed curves that actually achieves such an attack as well. So this shows that this paradigm is really able to improve the security of learning algorithms as compared to off-the-shelf learning algorithms that you might start off. So the key takeaways are that modern AI systems are more vulnerable to dynamic than static data poisoning, even though static data poisoning is what's mostly considered in the literature. Certificates establish an upper bound on the worst case impact of the attacker. And in particular, we show how to derive certificates for dynamic data poisoning attacks. And we show how to feed this back into the learning algorithm using a meta-learning paradigm so that we're able to establish more secure learning algorithms. I will end there, and thanks again for your attention. Here's the links to the paper and our GitHub, and the paper is to appear at AI Stats 2025, so please do catch it there if you're attending the conference. Thanks a lot, and happy to take some questions now.